Hi everyone, my name is Kuba Misiorny and I'll be talking with you today about language models and how they can help us connect people with the right information at the right time. My goal here is to describe the evolution of language modeling, a very technical subject in itself, but do it through a lens of practical applications. This way, I hope people that are deep in the algorithm weeds will be able to see the real-world applications of their work, and business people can develop a bit of an intuition of the magic that happens in the backend of applications that use NLP, natural language processing. All the use case of language model we'll talk about today will be presented through the lens of using the knowledge organization already have, but doing it in a better way. I usually give talks and workshops at this interface of technology and business worlds, which really means I translate one world to the other. So I'll be talking to tech people trying to translate requirements and business cases and how they affect technical decisions, and vice versa, trying to tell business people why something cannot be done for yesterday. Today I want to do something different. I want to be at this very fine line so that both the deeply technical people and the business people can benefit from this presentation. The key realizations we had at Untrite, my company, however obvious and mundane it might seem, is that all knowledge in an organization is connected. There's this invisible web that runs between all of the information on all levels, between documents, paragraphs in documents, or even words. A PDF report might mention a client's name. That then connects that report to the CRM objects about that client, all of the scanned invoice of that client, this client's account manager, etc., etc. And so being able to access, traverse, and analyze this web in an efficient manner, we believe is the holy grail of using knowledge in an organization. Some of those connections are explicit, they're manually crafted. A connection might be organizing files in a directory structure. So we know that all of the user manuals in this directory and all of the spare part numbers are connected with the machine A. Another way is keeping information in a dedicated system, like a SharePoint site for the communications team we see here, or keeping all of the customer tickets in the customer support systems. Those explicit manual ways to organize information are useful, of course. They've been used. It's been done like this for a long time, but they're only useful in this one dimension, the one that the organizer has designed. And so let's walk through a normal use case, a very typical use case in a company, for example, in a customer support environment. Say you're an engineer supporting a client that has a problem with the machine that you sold them. What kind of information will you need to efficiently and effectively help your customer? You probably need access to this client information that lives in a CRM system. You will need to know a history of issues this client has raised. That probably means access to the customer support system. You will want a list of machines that you sold to this customer, which lives in an accounting system, a history of issues with that machine, how to debug those machines, etc., etc. All this is leaves us with this emotion. So obviously it would be much easier if we had a system that would present all of this information to us automatically in one place, right? So that we could focus on the actual difficult part of the task, understanding the situation and then providing a solution to it. All we would need to say is that we're solving an issue for a particular client and a particular machine that they have, and this is what they said. So how can we do this? So we had this very base key idea of how we can connect information in an organization together to get this glimpse of the invisible web of information I have mentioned before. What we realized, and this is not a new realization by any means, so what we realized is that at the very base level, a way to connect a piece of information, a word or a paragraph in a document, together with a different word or different paragraph or different document, is to understand what that word or a paragraph means, and say things are connected if they're similar or they talk about similar things. I know this might sound too simplistic, but most elegant solutions are, fortunately, and I can show you how this can be done. So to explain this idea of similarity a little bit better, we're not after identity, so words or sentences that are exactly the same. We need to understand semantic similarity. So we're looking for similarity in meaning. And this is where language modeling is the key, and really where the recent advances in language modeling, deep learning powered language models, are useful. So what we want to be able to do is, using this description of a problem, a fuel engine reporting faulty, we want to be able to find an error state of this machine that is described as velocity monitoring broken. Those two sentences don't share any words with each other, so using a keyword search is not possible, and so on. But before we dive into this more detailed use case, let's explore the language modeling, what language models actually are, how language models evolved in recent years, and how we can use the latest innovation in this space to build something incredible in this semantic understanding space. So language models 101. An English linguist, John Firth, said in the 50s that you shall know the nature of a word by the company it keeps. And this is really the key principle of how language modeling works. Language models try to understand, model the world without any previous knowledge. They're not taught English or German. They are a clean slate when we begin their training. A language model learns to predict the probability of a sequence of words. They essentially predict the next word in a sentence. So if we have a sentence, I was happy too, the language model would predict the probability of the next word. And a traditional language model would learn those probabilities from essentially reading millions and millions of words and learning what kinds of words follow each other. But in our problem of language understanding, we're not really interested in predicting words and sequences, right? At least not directly. What we can do is utilize the way language models encode information internally to help us. What is gonna come next is a vast simplification, but one that needs to be done for this talk not to be 2 semesters long. Language models encode information about words using large vectors, which essentially means large lists of numbers. So for each word, a language model will compute a set of numbers. And this set of numbers for each word is called word embedding. So here we see a 4-dimensional word embedding. So each word, cat, is associated with those 4 numbers, mat with those 4, etc., etc. And so the idea behind the word embeddings is to capture with them as much information about the word as possible. A common way to think about word embeddings is to use them as coordinates in space. So each of the numbers in the word embedding would represent a location of the word in this one dimension. A well-trained set of embedding will place similar words close to each other in that space. So if we had a 2-dimensional word embedding, we could plot it on a graph like this. So words for cities would, like Paris or Berlin, would fall would cluster in one place in this graph. Similarly for words for food or body parts. A 3-dimensional embedding might look like this. And normally in a natural language processing scenario, we would have large hundreds or thousands of dimensions in the word embedding, but let's not try to visualize that. So these vectors can actually be based on a more comprehensive geometry of words. There's this famous example that if you take the embeddings, so the list of numbers for king, and subtract the list of numbers for a man, literally subtract the numbers from each other, and then add a embedding for woman, you would get an embedding of a queen. And it really does work, which is crazy. Remember, those language models that produce those vectors, they don't have any understanding of a language. They just compare what words appear next to each other, and they can come up with stuff like this. Another interesting example is if we plot countries and their capitals in this vector space. And if we forgot what is the capital of Poland, but we remember that Berlin is the capital of Germany, and we subtract Berlin, the embedding for Berlin, from the embedding from Germany, and then add it to the embedding of Poland, we would get Warsaw, or at least close to Warsaw. So you can see how those embeddings can actually allow us to discover new knowledge, or at least new knowledge to us. The model encodes this information in the model. And you can start to see as well how we can then move from keywords, literal keywords, to meaning, to build this information retrieval machinery. And so there's one last large piece of the puzzle I need to mention. So the first popular language models, like I described just a second ago, they would calculate embedding for each word in a vocabulary in this learning phase. So essentially when they are reading all of the information. And after that, those words, those vectors would be static. So unfortunately, this approach to word representation does not address a possibility that a single word might have many meanings. So a bank might be an institution that manages your money, but it might be as well a side of the river. And so a traditional word embedding would try to average out those meanings. So the vector, the word embedding for bank would be actually an average of those two meanings or more meanings, or all the meanings that the bank can have. And so this new wave of deep learning language models address this problem. Those models generate embeddings of words within the context of the sentence, because it's the context that actually changes which meaning we should use for that word. And this mechanism is called attention. And so attention allows us to look at the totality of the sentence. And of course, there's a German word for that concept, Gesamtbedeutung. So let's go back to our use case. A direct application of the ability to understand meaning of words is matching the meaning of the user's query with what the documents mean. So this is a direct evolution of the keyword search, where we would look for, in the keyword search, we would look for occurrence of words that the users typed in the documents of organizations. With the semantic search, we can achieve what I described at the beginning, finding this error state based on this query. Let's look more closely at this connection between the replacing of the speed sensor and the other documents that are connected with it. We can see that the model of the speed sensor, XYT46, is a special entity here. This model will appear in many documents across organizations. Detecting those connections would work out of the box of the vanilla language modeling, but we would get much better results if our system actually understood that this is a model of a speed sensor. And so we can employ another natural language processing technique, which as well use language models and word embeddings to do that. And this technique is called named entity recognition, and it formally seeks to assign a label to a word or phrase. So say we are an engineering company employee and we need to process hundreds of comments like this to our company designs daily. A named entity recognition system would find that an FS2005 is a regulation code, the drawing 4 is actually a link to a PDF with that drawing, and the boiler X3-5 is a machine model, and it can link us to all of the information about this machine. Knowing those entities in this text can connect us with the whole web of information in the whole organization. And we can do it both if this ontology, for example, of the machines is explicit. For example, the company has a tree of all the machines they make. We can link directly this text to this ontology. Or if the ontology is implicit, the company doesn't have a explicitly defined ontology, It can be derived automatically from the structure of files and structure of information of all the other documents in a company. In either case, the name recognition would connect us directly with this company information structure, as we can see in this overarching diagram. And all of this actually can be done automatically without any human intervention. The system just needs to have a line of sight in those documents, SharePoint, shared drives, customer support system, etc. And of course, we just scratch the surface of how powerful those technologies are and how they can be applied to make our lives easier. I hope this introduction was enough to pique your interest. And if you'd like to know more about this, just write me an email or connect with me on LinkedIn. Thanks. Bye-bye.